Okay, it's time to begin. And this is our second lecture. So if you're just coming in for the first time today, I just want to remind everybody to always go to the calendar. Just Google Stat 100 and then click on the calendar, and you'll see what's due. So this Friday, reminder, heads up, if you haven't done the pre-lectures yet, do them. They won't take you that long, and certainly do the bonus survey. It will just take a few minutes. Those are due at midnight, 11:59 and 59 seconds on Friday. Okay? Now, after today's lecture, you'll have everything you need to know to do both homework 1 and homework 2. And they are due 11:59 on Monday and Wednesday. All right, so I usually open up the homework well ahead of time. So right now, I'll try to open up homework 3 and homework 4 this weekend. Now, if you do it ahead of time before I lecture on it, I probably won't go and look and answer your questions. I'll wait till after I lecture on it. But some of you have had stats before, can just figure it out from the pre-lectures or just from the notebook and might want to try it. You have multiple questions. So you can always do your homework. Also, feel free you can do your homework while we go over the problems here. There's probably enough time. You can always do that too. And that way, if you have questions on the homework right after the lecture, you can ask me right away. All right, so let's begin. So remember where we left off. We were talking about confounders in observational studies. So let's go to the document camera right now. And let's look at this. Okay, so recall that these confounders only happen in observational studies because what are they? These confounders are their differences. Maybe I should write this down. Differences, they only happen in observational studies. And in observational studies, since the treatment and the control groups chose themselves, there's bound to be differences between them. So in observational studies, remember, the treatment and control groups are different to begin with. Before the treatments, they self-select. So the treatment and control groups start off different to begin with. Start off different. So why is that a problem? Because they're going to be different in ways. Remember, you divide them into groups when you do an experiment, and you want them at the beginning to be as alike as possible because the only difference is going to be the treatment. And then you can see at the end of the study if they're different in their responses, if their responses are different, well, then it had to be the treatment because they're the same to begin with. But in observational studies, they choose themselves, so they're bound to be different. And if those differences influence the response, they mix up the study. So confounders are differences between the treatment and control group from the get-go that influence their response. So we can't tell whether it's the confounder or the treatment that's causing the response. That's the problem. So why is this important? Why am I even talking about this? For a lot of reasons, because a lot of people are going to probably be, you might end up in some kind of research field where this is going to be very important. But even if you don't, just reading, being a knowledgeable citizen, just making decisions about many things in your life depend right now on understanding studies. And in many observational studies, when people see two things associated with each other, they conclude causation. And all the time, because our minds are looking for reasons, right? So it's very important to think about what possible confounders would be. Okay, what's really going on? What could be the causal pathway, really? So that's why we're spending so much time on this. It's important just to make decisions about almost everything in your life these days. Okay, so I'm going to start off with this kind of ludicrous, absolutely, sort of a very, very clear-cut example where you know already there's a confounder, and you probably already know what it is. Just so you can get the logic down And you can remember this iconic example to help you think of ones where it's much harder to understand, where you don't know what's going on. So that's what we're going to start with to understand what the idea here. Okay, so this is the extreme example. Lighters and lung cancers. Observational studies show that people who carry lighters have a higher rate of lung cancer. Okay, so does that mean that lighters cause cancer? Well, maybe. And if so, how would they do that? But there's another possibility that lighters don't cause cancer at all. Okay, so first let's start with this one. The first possibility, okay, so we'll say number 1 here. And so we have this, we have lighters, which is the treatment. That's the treatment. And what we're trying to do is we see this link between the treatment, the lighters, and lung cancer. That's between treatment and response. It says lung. Gosh, I'm sorry, my handwriting's bad. It doesn't need to be anything like that. Okay, sorry about that. I'm going to try to get a different pair of glasses on here and see if that helps. Okay, let's see if that works. Didn't bring one. All right, I'll have to make do with this one. Okay, so the idea is you see an association between the treatment and response. So one possibility is that there's this, that the lighters are actually causing the lung cancer, in which case the arrows would go this way. Okay? So if so, the arrow in the diagrams on the left, the box, I'll say, on the left represents a possible causal link where the arrows go this way. The lighters maybe have something in them or somehow trigger something that causes the lung cancer. That would be a causal link. All right, so let's write that in. That would be a causal link. But there's another possibility, let's read about that, that the lighters aren't causing the cancer, right? But then why would people who carry lighters get more lung cancer? Why are we seeing this association between the treatment and the response? Why are we seeing this relation between lighters and lung cancer? We're seeing this in our study. People who carry lighters have a higher rate. So if lighters aren't doing it, why would we see this association? Well, one possibility is that right here, let's put a box in here, that there's something else causing the lung cancer. Something else, a third factor that's not caused by the lighters. A third factor that's actually probably causing people to carry lighters. So that, and this is called a confounder. Or a confuser, a confounder, confounder. And that's, so why is this important? Because we want to tell people, hey, if it's this situation, we'll tell people to not carry lighters, carry matches, in which case their lung cancer rate will be reduced. But if it's this situation, if we tell people to stop lighters, it makes no difference because there's some other cause. Lighters is just a marker for this other cause. Does that make sense to people so far? Even though I have bad handwriting right now? Okay, so now I'm going to try to improve this handwriting. Okay, so now, right now, so we have either this first situation or this second situation, and there's another possible thing that people do all the time. They just look for another cause of lung cancer that has nothing to do with the treatment, another cause of the response. They say, oh, it's so complicated. Lung cancer is caused by many ingredients, many different possible factors, and they say, okay, that could be mixing up our study. That could be the explanation, but no. We're trying to explain why we see this association between the treatment and the response. So we're looking for either something that is linked to the treatment, another, some third factor, a confounder, or else we're wondering, like, an explanation here. These are either going to be right down here. I'm going to ask you to think about what could be a possible explanation if it is causing it. and what could be possible confounders, and what are just other causes, but don't have anything to do with the situation here. Okay, so that's what I want you to think about. So why don't you try doing these on your own and see what you come up with. I'll just read it together. Below are possible confounders that would fit inside this mystery box, mixing up the result, making it look like lighters are to blame when they're not, or possible causal links that would explain how. It would fit right in here, that it would explain how, or neither. Like other causes of why people might get cancer, but nothing to do with lighters. So I want to see if you can do this on your own first, just intuitively, and then we'll walk through it. Okay, so let's just start with the first one here, all right? So what you remember, what you're thinking about, okay, we see this link between the lighters and the lung cancer, and we're trying to figure out, and then we have this box here with genetics. Okay, and then we're going to read this explanation here, because this is going to, some things can be either causal links or confounders, depending on how you're thinking about it. So I'll say, answer these questions, answer assuming only the given information. Don't bring in outside information, because we're just trying to look at the logic of the situation, not testing your knowledge about stuff, outside stuff, okay? So right now, some people are more genetically, some people are more genetically prone to lung cancer than others. So genetics can influence whether or not you get lung cancer. But does genetics, there's no mention of the lighters. There's no link at all. It's not like genetics are going to influence whether you choose a lighter or not. So there's nothing here at all. So what would you, since there's no mention of lighters at all, what would you choose here? Neither. Okay? Does that make sense? Okay, let's try the next one. Lung cancer rises with age. Again, you have the lighters, and you have the lung cancer. And this is what we already know. We see this association, right? Could this be an explanation for it, age? Could age be an explanation for it? So we'll try age in here. Well, let's see, lung cancer rises with age. Okay, so older people are more likely to get lung cancer. All right, but again, no mention at all of lighters here. If older people are also more likely to carry lighters, then that could be what? That would, if when you got older, it was maybe like in my day, it was cool to carry a lighter. Flick your Bic and all that stuff. So maybe like older people are more likely. If that was the explanation, then maybe that could be a confounder. Okay? But I didn't give you that explanation, so that's neither. All right. Now, smoking cigarettes. People who smoke cigarettes, I think you know this one, people who smoke cigarettes, smokers, putting smokers in the box, and we know, and it says right here, that causes lung cancer. And they are also obviously more likely to carry lighters. So that is clearly a confounder here. That lighters are a marker for smokers, right? That this is why. So we would never give advice, hey, don't carry the lighter. If will help your health. No, it makes no difference whether they get rid of this because the arrow is pointing the other direction. It's not causing people to smoke. Do you get it? So that's the confounder. And what about this one, lighter fluid? Okay, so it says inhaling the fumes from the lighters can cause cancer via lung damage. So that would be how the lighters actually have something inside them, carcinogenic fumes, which leads to lung cancer. So that is obviously the causal link, right? And the last one, radon. Radon certainly is a risk factor for lung cancer, so radon does cause lung cancer. You don't even have to know that. You just read it here. You assume this is true. But again, there's no link to lighters, so it doesn't have anything to do with it. All right, now I know that was super easy for you, and probably most of you got it right, but I want you to understand this so you can apply it to other more complicated situations. Okay? So let's turn the page. So now that we know that we've identified smoking as a possible confounder, that doesn't mean that two things can't both be. That doesn't eliminate lighters from any responsibility. Lighters might also be a cause. They could both be a cause together, right? There's not just one cause for things. So we want to eliminate. What we want to do now is to eliminate, to stratify, so that we can eliminate, or another word, control for the effect of smoking and see if there's any association that remains between the lighters and the lung cancer. Okay? So what we're going to do is we're going to stratify. This is what we're going to do here. Stratify to control for the confounder. And what does control mean? Control for the confounder? It's actually control for, control for. What does that mean? It means eliminate the influence of the confounder, okay, on the result. Okay, so then stratify to control for, eliminate the influence of the confounder on the response. Sorry about that. Okay, so you should tell me. Somebody should tell me here, like, hey, move the camera. Okay, in the future? All right, so now stratification. What do we want to do? We want to break the population into subgroups where the confounding factor is the same. Remember our goal here. We want the treatment and control group to be the same. They're not. They're not the same. Why are they not the same? They're not the same because if you have your treatment group here, the lighters, and the control group here, which is the no lighters, right? Lighters and no lighters. But they're not the same because the treatment group also has more smokers. The group that carries the lighters has more smokers, and this group has less smokers. And this is our confounder right here, smoking. So we can't tell on something, what are we measuring? What does the scale measure? This scale is measuring the lung cancer rate. So between here and here is the lung cancer rate. And we're seeing that those who carry lighters have, this is what the effect we're seeing. The treatment has more lung cancer than the control group. But they also have more smoking. So it's confounded, it's confused. So we want to separate out the effects of these two. How do we do it? We do it by stratification, which means dividing stratifying the population into subgroups where the confounding factor is to the same. So to make the treatment and control group, treatment and control, the lighters and no lighters, the same within each subgroup, because they're not the same to begin with. Right? So we're going to take non-smokers. These could be the non-smokers right here. And within that group, we're going to compare the lung cancer rate of those who carry lighters to those who don't. You know, people who don't smoke cigarettes carry lighters for other reasons. And so, you know, there might not be as many of them. There won't be as many of them. So there'll be people, most of them won't have lighters, right? But there'll be some who have lighters. And we're comparing the rate of lung cancer. Not the numbers, but the rate of lung cancer. So that controls for the different numbers. We're not balancing the numbers here, how many. We're saying how many per 100, okay? So even though there's fewer who carry lighters when they don't smoke, it doesn't matter because we're comparing rates. And we do that, and now smoking can't be confusing things because nobody's smoking here. It can't be. So we have eliminated the confounder and made the groups more alike. They're the same, no smokers and no smokers. And the difference here is just the treatment and the control. Do you understand? Does that make sense to everybody? So that's what we're doing. We're comparing the lung cancer rate of those who carry the treatment group to the control group within each subgroup to make them more alike. And we'll do the same with moderate smokers and heavy smokers. Okay, so smoking is out of the picture now. They smoke the same amount, but you still have the treatment and the control group, treatment and control. Now, in this case, what happens when this is done, when we include smoking, we call it as a, when we control for smoking, that difference goes away. So in terms of the lung cancer, sure, the non-smokers don't get much lung cancer, but it's because they're not smoking. So this is, the more you smoke, the more you get the lung cancer, right? That's why they're way up here. But within each subgroup, lighters make no difference. Lighters only make a difference and make it look like that when you don't divide the groups up because they get mixed up. People who carry the lighters are also heavy smokers. So that is the idea. Any questions on that? So we stratify to make the groups the same because they start off different. That's the key idea, that observational studies, I can't emphasize this enough, observational studies, treatment and control groups are different. Not just different because they have the treatment, but different in other ways, right? And we stratify to control or to eliminate that difference, and to make the treatment and control groups alike. On the confounding factor, to get rid of the confounder, as far as the confounding factor goes. There could be other confounders. This is complicated. Okay, so that's the idea. So now, so there are basically two ways to control for confounders, and they only happen in observational studies, as long as your randomized experiment is big enough and you block properly. You'll get accidental differences in randomized studies, but you won't get systematic ones, like systematic ones. No matter how big the study is, this is still going to remain in an observational study. I don't care how big the study is. If it's a confounder, if it's a systematic difference, it's not going to go away. Whereas accidental differences, random differences, go away with a larger sample size. That's why randomization is so important. So there's two ways. One is stratification, like we did above. And another way is modeling. Which is when we get to regression, we're going to create models to see what would predict lung cancer, for example. And if we had, if it looked like lighters predicted it, then we would include as another predictor variable, smoking. So including the confounder as an independent predictor called a covariate in a regression model. And that's going to be in chapter 30. We're going to compare doing these two things. Okay, so what happened here? What if these didn't go away? What if it didn't go away? Like sometimes it might go away here, it might go away here, but among heavy smokers, maybe it has a synergistic effect or something. Maybe that the lighter fluid and the smoking together activate something. or it only affects people who are already smoking. So then you might see it in certain groups, not in others. I'm just giving you the simple example here. But here, since the groups became balanced, what can we assume? What can we conclude? Here, since the groups are balanced, within each, since the groups, the subgroups are balanced, since the subgroups are balanced, we know lighters cause cancer. More use right there. Lighters, look what I said, look what I just did. What should I put here? Smoking. So dumb there. Smoking causes lung cancer. Smoking causes lung cancer, not the lighters. So you could say the confounder is causing the lung cancer, smoking the confounder, not lighters the treatment. Does that make sense to everybody? Raise your hand if it doesn't. Let's say they were still tipped the same way. Well, then we could say, well, smoking's not a confounder. Does that mean we can conclude that lighters? No, we'd look for other confounders. This is a complicated thing to do. I'm just giving you the logic of it. There could be multiple confounders. Okay? Let's move on. Okay, so now we're going to look at examples. So this is much more common, that you see these studies, like sunscreen causes skin cancer. You might see headlines like that. Or smoking causes liver cancer. And if they're observational studies, you have to find, you can't just conclude you can't conclude just because you see an association. It's a causal one. So you have to think up confounders on your own. So that's what you're going to be asked, that's what I'm asking you to do here, okay? The following studies show association. Do they also show causation? What are the most likely confounders, and how would you adjust for them, okay? So let's think about it. Remember what our goal is. It's going to be to eliminate, in these observational studies, to eliminate the confounders and see if the association still remains between the treatment and the response. So what should we do here? So let's see what it says. To find the confounders, list the differences between the smokers and non-smokers, besides the treatment, right? This is the treatment, and this is the response. So we want to list, there's differences between people who get the treatment and people who don't, between the smokers and the non-smokers, because they've chosen themselves, they've self-selected. So we have to think about differences between them that could be influencing our results, that could be causing, for confounder, it would be a difference that a difference here that causes the response, which is liver cancer. It causes liver cancer. That's what we're going to put in here. And that's the response. And also, somehow, is a difference, or causes people even to do the treatment, okay, which is smoking. Causes a higher rate of smoking. That's the treatment. So let's think about it. What could possibly be a difference between people who decide to smoke and people who don't, that you know could cause lung cancer, liver cancer? Anybody have any idea? Yeah, in the back? Yeah, that's a great one. Drinking would. Because we know that drinking alcohol's a poison, so it's going to affect your liver for sure. So drinking is a great one. So, but also, people might not know, but smokers drink more alcohol. They go together very well. Drink more alcohol. And these tend to drink less alcohol. So what would we do? we'd say, okay, let's test it in here. So alcohol is a known cause of liver cancer, and alcohol is, even people who don't smoke very much often in a bar start smoking, or at least they used to when that was legal. So they go together very well. I guess it just loosens your inhibitions so you start doing all sorts of stuff you would do more of. They're bad for you. Okay? So that is a great one. So how would we control for this? What would we do? What would we, how would we know whether this is certainly a good first guess? And then what would we do? How would we control for it? We'd break what? We'd break the population into subgroups. And then compare treatment and control within each subgroup. To subgroups. And what would be the subgroups? No alcohol, we could do the same thing. No alcohol. Moderate alcohol, however many you want. You just want them to be the same and heavy. Lots of alcohol, high alcohol. And then within each subgroup, we would compare the treatment versus the control. We would compare smoking. Smokers, nobody's drinking here. Do smokers have a higher rate of liver cancer than non-smokers? Same here and same here. And it turns out it goes away that smoking does a lot of bad things for you, but liver cancer isn't one of them. Okay, so let's try this one now. Studies have shown that people who use sunscreen have a higher rate of skin cancer. Does that mean people should stop using sunscreen? That it's dangerous? Maybe. It might be. I mean, there might be something inside sunscreen that is carcinogenic. And I remember there was at one point. That's why they always say PABA-free. They thought that PABA was some carcinogenic element. Anyways, first, this is an observational study. They didn't randomly assign people to use sunscreen or not. And so what do we have to do? We have to think of differences between the treatment, the people who use sunscreen, sunscreen users, and not as. So the people who use sunscreen, that's the treatment, and no sunscreen. We have to think about differences between that's the treatment and that's the control. That could what? That could, we want differences, this confounder, that both causes, that we think could cause skin cancer, something that you think could cause skin cancer, right? And there's a difference here. So is causing people to use sunscreen or not? It's not something a causal link would be something, a carcinogenic ingredient in the sunscreen. So can anybody think of anything that would fit there? That would be a possible confounder? Say again? Oh, where they live. Yeah, why? Because some places are sunnier than others. Exactly. Some people, where they live or how much sun exposure they get, right? Is that what you mean? How much sun exposure they get. That's really a good one because if they're getting a lot of sun exposure, right? So we could just say people who use sunscreen get exposed to the sun more. They use it because, right, so they have more sun exposure. Why would you put on sunscreen if you weren't out in the sun? And this is less sun exposure. That's a great one, right? So sun exposure. Yeah, if you're out in the sun a lot, you're going to get skin cancer. And if you're out in the sun a lot, you're going to put in sunscreen. So sunscreen, we would never tell people if it was the sun that was causing them. Sunscreen is a protectant against this that helps reduce sunscreen. So you might see this. This would be very important to recognize that it's not the sunscreen, that it could be that it's the sun exposure. And then if people stopped using sunscreen, they'd get more skin cancer, not less. So that's a great example of why it's so important. And not just to listen to the studies, think about it. And so we would stratify on people and look at people who are in the sun a lot and compare people who are in the sun a lot, those who use sunscreen, with those who don't. Does that make sense? All right, let's do another one. So this one was from the study that we're doing right now on looking at learning outcomes of online versus in-person. And we've been doing this for a few years, and one thing we saw in Stat 100 was that the online students taking the same exact course in Stat 100 compared to the in-person students end up doing significantly better on the exams. So when people see this, when I first present these results, everybody says, well, because the courses are completely identical, that's an argument. People take that right away as an argument for online learning being better. Something about the online learning that people maybe is better, right? But we didn't randomize this. This is not a randomized study. So there's going to be differences. So we have to, this is actually what we have to do. It's a lot of work. So what we have to do is we have to look at differences between the treatment, which is, we could say is online because it's the new thing, and the control, which is in person, and make sure that there aren't possible confounders. So that was, we were using survey data to do that and other data we have on the two groups. And one thing that we possibly thought was, okay, maybe, so we're looking for something that would both cause students to get better grades at the end, to get higher exam scores, you know, to do better in the class, so better grade at the end. And something would do that and would also maybe cause them to choose the online. Cause them to choose the online. We're thinking, this is what we're thinking of. You know, we're thinking of, we tried to control for a lot of different things. And the only thing that we really found so far that's really significant was higher ACT scores. So people who are, if you think of ACT scores as like whether you're better at math to begin with or not. Okay, so the people who are better at math to begin with have higher ACT scores. Maybe in Stat 100, it's not the same as in 200. But in Stat 100, they may feel very confident about that course, about being online, and feel like they don't really need to be taught as much. So in Stat 100, there's pretty significant differences in their beginning math ACT scores. So you could think of it as higher. So on the average, the people in the online have higher math ACTs, and they have lower. It's a significant difference. And so we think that once we control for that, so that means like math ability, if you think of it that way. So the people with the higher, you know, who are better at math to begin with, higher math ACTs, are choosing the online, and that's probably going to cause them to do better. If they're better at math, they'll probably do better in the course anyway. So they'd probably do just as well if they took the in-person. It might not be anything about the online, but it's pretty complicated. We haven't really, we really want to find out what's going on, and the only way to really find it out is to randomize. But when we do control for their compare people with the same ACT scores, then the difference goes away. So, and it doesn't with most of the other things we've looked at. So it might be that there really is no difference between the two types of learning. All right, in Stat 100. Okay, now let's move on. And any questions so far? Okay, so now in observational studies, you can have such extreme confounding that when you break them up into subgroups and control for the confounder, you can get an opposite result. And there's been a few examples. This doesn't happen that often, but there's some classic examples of this. And one of them is this classic study that was done at Berkeley. All right, so Simpson's paradox only happens in observational studies, and it's confounding that's so dramatic that the results are reversed. So let's look at this example. So back in 1973, Berkeley was accused of sex bias in their admissions to graduate study. And the evidence was that 8,442 men and 4,321 women applied for admission to graduate school at UC Berkeley, and 44% of the men got in, whereas only 35% of the women. Now that's a significant difference. And the first thing that might jump out at you and say, well, 44% got in because more applied. That's what a lot of people think. But these are rates. They're not the numbers that got in. 8,440, this is per 100. So for each 100 men, out of those that applied, 44 got in. And for each 100 women, 35 went in. So when you compare rates like this, it takes care of the difference in the numbers here. So that wasn't the reason. Okay? Now, is this a controlled experiment or an observational study? I should say it wasn't because, maybe, because I'll probably ask that on exams. I want you to be aware of that and just be sure to not think that would be the reason. So it's not because more men applied. Since the results are in rates. If we compared absolute numbers, sure. Rates or percents, not absolute numbers. Okay, now, is this a controlled experiment or an observational study? They didn't randomly assign people, males and females, to apply, so this is obviously an observational study. Assuming that men and women are equally qualified, is this evidence of sex bias? Well, they for sure thought it was, but we know better, right? Because it's observational data. They thought for sure it was. It might be. We don't know yet. And they said, okay, it's clear evidence, and it looks like it because, look, I mean, it's evidence that more men get in. The percentage of admission is just clear cut. Men get in more. But is it because of bias? That's the question. Or is there something else going on? And they thought it was because of bias, and they wanted to find out which majors were the worst offenders. So they went ahead and they broke it down by major, thinking that all of them would be discriminating, but some of them would be discriminating a lot more than others. So let's see, let's look at this. And so they had like about 30 majors or more, but here's just the top 6. All right, and so in major A, let's compare. Are they discriminating against women? Is there sex bias against women? 82% of the women got in versus 62% of the men. That's favoring women, right? This is favoring women. How about the next one? Favoring women, right? Not as big a difference, but favoring women. How about the next one? They're about the same, a little bit for men, about the same. Women's higher, about the same, about the same. But there's not any that have they're significantly biased against men. If anything, significantly biased against women. If anything, the sex bias is against men. So what's going on? What is going on? This overall rate right here, if you look at the totals, the overall rate for all the majors, not just these, what we got was 44% here, and here the percent of women admitted was 35%. Okay? So out of each 100 women who applied, 35 got in, whereas 44 men got. But if you look at any particular major, and if you went through all the 30 majors, we couldn't find it. They couldn't, so they were baffled, and that's why it's a paradox. That's why it's called a paradox, that the overall result is different. If anything, they found bias against men, and that's why it's a paradoxical result. Okay? They found that most majors show favoritism to women. So that's your paradox. And it is baffling. It really, really is baffling. So, and it's kind of hard to see what's going on, but let's look at this. Basically what's going on is look at these majors. Majors A and B are relatively easy to get into. Over 50% of the people who apply to them get into them. So these are relatively easy majors. And these, C through F, look at them. They're all pretty, look at F, it's really hard to get into. C through F are harder to get into, are the hard majors. All right, now where are the people applying? If you look here, if you look at all these numbers, most of the women, in fact 93% of the women, are applying here, are applying to the hard majors. And if you look here, look how many more men are applying to the easy majors, right? And if you look here at these two majors, look at here, if you added these up, look at this as a percentage. This is over 50% of 2690. So over 50% of men are applying to the easy majors. Okay, easy majors. So what's happening is, if you adjust for major, like when you break it down, women's overall admissions rate, if you know, there's no sex bias at all. We see that when we adjust for major. None. That goes away completely. This 44, this favoring men, goes away completely. In fact, it gets tipped the other way. So it's just worse because women are applied to the harder majors, and are proportionately more women applied to the harder majors, where it's harder for everyone to get into. So in other words, if they blinded them, if they took off their names and the admissions directors, the admissions committee didn't see who was a male or who was a female, you'd get the same results. It's not because they were female. It's not because of bias towards them. It's because they applied to harder majors. Does that make sense? Okay. So you can read about this study. So that's an example of Simpson's paradox. And then here's an example I made up that as one that will, because if you're familiar with The Simpsons, one that will help you remember what Simpson's paradox is. And since it's called Simpsons, I thought it would be a good one. I put it on an exam, and then people all got it right. I mean, they understood it so well, so now it's here to help you learn it. All right, so Bart and Lisa Simpson decide to take college courses online. And the courses are divided into two groups. Group A is for those who want to be challenged, so they're hard courses, right? Group A is hard courses. And Group B is for those who are already challenged. They're easy, okay? So these are easy courses. Both groups cover the same subjects, but at a different level of difficulty. So Group A courses include Japanese, physics, calculus with several variables, and Group B courses include Japanese movies, physical education, calculators with several fingers, and stuff like that. So here's a chart that shows how they did, all right? So you notice that overall, now Bart and Lisa chose the courses. Bart chose to take only one hard course and 9 easy ones. And Lisa chose to take 9 courses and one easy one. So if you look at their overall GPA, who does better? Bart does better overall. So who does better overall? Who has the overall? Bart. But remember, this is an observational. They chose themselves, so don't trust the overall results. We have to break it down by subgroups. This is an observational study. They chose themselves the courses. They weren't randomly assigned. So don't trust the overall results. You have to compare apples to apples. Break into subgroups. To compare apples to apples. A's to, group A to group A and group B to group A. I don't know if you've heard that expression, but apples to apples, oranges to oranges. You want to compare group A courses to group A, group B to group B. So now, Bart does better overall, but look at the difference who had the higher GPA for the hard courses. Well, there's a dramatic difference. Bart can't do the hard courses, but it's very hard for anybody to do well in them. So Lisa only got B's. So Lisa. And now, who did better in the group B courses? Lisa again. Almost everybody gets A's, but she got a complete straight A. Okay. So now the question is, which one do you trust? Let's say Bart and Lisa both decide to take one more course. This time, they'll both take the same exact course. Who would you expect to do better? So you circle one of those. Which one do you think? Okay, so what did you say? What did you say? How many people said Lisa? How many people said depends on whether? Good, everybody said this. All right, Lisa's going to do it. Side by side, Lisa will do better. So don't trust the overall results because the treatment and control are different. And the overall percentage is misleading here. And that's why high schools, I don't know if you went to a high school where they weight the AP courses differently or honors courses differently, it's exactly for this. Because if they didn't do that, students could take really easy courses and colleges would, when they look at your overall GPA, they wouldn't be able to, the students who took the easy courses would have a higher GPA. Because they know not to trust that overall GPA, so that's why they weight your courses, your GPA in high school. Any questions on that? Does that make sense? All right, so now we're going to look at randomized experiments that start off, they don't have any confounders to start off with, but they could develop them later on. So this is basically when a good randomized experiment can go bad, how it can go bad. So just because it starts off with the randomization, it can end up being observational. So you can get observational data even from a randomized experiment if you don't keep the original randomization. This happens all the time when people drop out of studies. So what do you do with people who drop out of a study in a randomized experiment? Do you include them or not? Let's think about it. So here's an example of observation. So here's an example of a randomized controlled double-blind experiment, perfect ideal experiment. It was done on middle-aged men with heart disease to see if this drug clofibrate would prevent heart attacks because it lowers cholesterol. So the patients, these were patients at high risk to get a heart attack, and they were followed for 5 years. And the death rates between the two groups were basically the same at the end, right? So they randomized them, and this is what they got at the end. So it implies the drug didn't work. That wasn't a significant difference. But then people do this, and there was a lot of debate about it. But not everyone took their medicine. You know, not everybody adheres to the treatment. If you look at just the subjects who faithfully took the clofibrate, called adherers, their death rate was only 15%, right? Compared to 25% for the non-adherers. So people argued, well, hell, heck, the drug can't work if you don't take it, so this should be the relevant comparison. But remember, we have to stick to the randomization. So they were randomly divided to begin with into this group and that group. They didn't know which group they were in. It was an ideal experiment. And these right here are self-divided, self-selected groups. These right here. So these are going to be different from each other. Adherers are going to be different from each other. So if we look at just the adherer, if we look, this isn't a good comparison. Because even when there was a placebo, nothing's going on here. The people who adhered had a lower death rate. They're probably more responsible to begin with. They take their medicine every day. These are probably more likely to be slackers, so they're likely to slough off in other things that are health-related, like their diet, their exercise, etc. So which comparison should be used? Adherers versus non-adherers, everyone in the treatment versus or something else. Now, a lot of people, you know, so you can think of these as more responsible and these as slackers, and that would explain these results. So people would say, well, why don't we just compare these, you know, the adherers to the non-adherers, right? Or, no, not do that. That's ridiculous because they're different. So why don't we compare these two? Adherers, apples to apples. And same here. Like we stratify. Why don't we just stratify like that? Anybody think that's not a good idea or a good idea? And why should we use this result? Why don't we just use these? Or maybe we shouldn't. Well, we know we shouldn't use this. We shouldn't. This is bad. This is bad because they're different. They self-selected. So everyone in treatment versus everyone in control, or this, they look like it doesn't make any difference. So it looks like you could do either one. But the problem with that is that let's say this drug, we want to keep the groups as alike as possible, but there might be differences between these adherers. People who adhere here and people who adhere here. This is just a sugar pill. People who adhere here might, or drop out here, might do so because there's really bad side effects, or they could drop out for different reasons. And also, sometimes you don't have this data. So the idea, we'll explore this a little more in the next two examples, but it's much better to compare everyone in the treatment group to everyone in control. I mean, it's important, it's interesting to look at this to see if they're different. And when they're the same, it really doesn't matter that much. But as a rule, sometimes they're going to be really different here. And as a rule, you want to stick with the original randomization because you're going to introduce bias if you start letting the groups break that randomization. And they're self-selected groups here. So let's look at two examples, and you'll see why it's very important to compare everyone to everyone. So suppose the above data came from a study where it's impossible to have a placebo, the same exact data, like, for example, a study to see if an exercise prevented heart attacks. Then we wouldn't know who was an adherer or non-adherer here. All we see is the total. So you have all the hard patients here. You randomly divide them. And this is, you should compare everyone to everyone. Because here, they're divided by choice. It's a self-selected group. Okay, and here we have nothing to compare it to. So that's pretty obvious that when there's no, you can't, what people do all the time is this comparison. And that is the worst. So comparing, in this case, and you'll see it, you have an example of this like in the voucher study, which is in your homework, comparing 15% adherers in the treatment versus 21% is terrible. Because you're comparing, in this case, you'd be comparing the responsible people to everyone. Right? So the responsible people, the ones who adhered, to everyone. So comparing adherers and treatment to that is terrible. Does everybody understand why that's terrible? You can see it here. This is a terrible comparison. Any questions on that? Because these are, remember, these are like the responsible people. The ones who've been identified as being adherers. And the 21% is everyone. So that's going to be completely favored towards the treatment. Does that make sense? Yeah?
I get why you can't compare adherers to everyone, but why can't you compare adherers to adherers?
Well, here you can't, right?
Yeah.
But yeah, that's what I'm going to explain now. Excellent question. They're the same, why not? Because if we're assuming they have the same motivations. Let's do an example. Here it's very hard to see, because you get the same result anyway. But let's look at a different, let me explain why. And here you'll see here. Why not here answer, so glad you asked it. Here's this question. Why not compare adherers in treatment to adherers in control? So remember why we do these randomized clinical trials. We need to make sure the groups we compare are nearly identical before the treatment starts, okay? And they start off nearly identical. Because adherers select themselves, there may be systematic differences between those who choose to adhere in the treatment group versus those who choose to adhere in the control group, since what they're asked to adhere to can be so different due to the drug side effects. And this happens all the time. These differences between the groups could confound the results, making it hard to determine whether it was the treatment or the self-selected differences that caused the results. So I made up this example to show you. So here's an example where the self-selection introduces so much confounding that comparing adherers versus adherers gives the opposite results as comparing everyone to everyone. So here's an example of something I didn't do, but something I've thought of doing and I'm scared of because of these results, potential results. Okay, a randomized controlled double-blind experiment, pretend, this is hypothetical, I didn't do it, was done to see if offering more and I didn't read about any experiment like this, if offering more challenging bonus problems would improve student performance in a large online intro class. Half the students were randomly assigned to the more difficult problems, treatment, and half to the standard problems, control, and they didn't know which group they were in. At the end of the semester, right here, the averages of the two groups were compared, 80 versus 84, and it looks like the challenge group did worse. But then when I look at the results, I could say, well, not everyone did the bonus problems. If you look at those who faithfully did the bonus problems, the adherers, and the two groups, the challenge group did better. So it would be paradoxical. People who did the bonus problems did better, but the overall result says the standard bonus is better. So why would we see results like this? Again, what are we thinking here? Do you understand why this might happen? Look at this. Look at the dropout rate here. So 400 people did the bonus problems here, and only 200 did it. So here, the reason why the overall is probably a benefit is because more people did the bonus problems, and bonus problems will help. But here, so few of them did it because they were hard. There's such a big reason to not adhere because they got discouraged. When I do the challenging ones, people get scared. This This is why people say, why don't you make things harder? Sometimes it has a bad psychological effect in intro classes. Terrible. And then they think things get too complicated too quickly, and they think they can't even do simple stuff. And so this is what I'm really afraid of, making problems too hard, because I see this all the time. So people just drop out or give up or whatever. So here's the random. This is the treatment. I'm thinking about doing this. This is the control. They're randomly divided. And these are different, the adherers versus the non, but they're different motivations for dropping out. So these kids, you could look at them, you could say they're smart kids to begin with. So look at this. So these people are smarter, and they were easier, so they didn't drop out. And this is more or less more average, less smart, more average, more everyone. And so they included more average. These were just the top students. So you can't tell if the challenge bonus problems helped them or they were smart to begin with. It's very hard. It's all confusing. The only thing I can decide as a teacher is this. And it looks like I probably wouldn't do them. Does that make sense? Does that answer your question? This is really important in drugs because drugs have different side effects. Then, you know, and people drop out for that reason. Okay, well, let's see. So, so what should we do? Everyone in treatment, everyone in control. This, by the way, is called intent to treat, and it's a very, I think I wrote that down here. Oh, no, I didn't. Where do I write it? Yeah, right here, intent to treat analysis. And it's standard in medical practice. Never compare groups where the treatment might affect what group somebody lands in. If you look at subgroups that have been divided before the treatment, like male and female, that's okay, but not subgroups that have been divided that are a result of the treatment. Keeping the original randomization by combining all those originally assigned to treatment, whether they adhere or not, is called intent to treat, and it's standard practice. Okay, so you will always want to do, as just a rule of thumb, everyone in treatment, everyone in control. All right, I think that might be it. Let's see what else we have to do today. Oh, you know what? I don't really want to get through this notebook, so I'm just going to keep going that way. This next part is so easy, and then we can cover the whole book. Do you mind? I know you mind, but we have 10 more minutes, right? So I don't want to waste it. All right, this is so easy. Now we're leaving this experimental design behind, and read these studies. These are really important. You know, read these on your own, and they're a very good way to study for exams. They're good summaries, but I don't have to read them now. Okay, now, descriptive statistics. Okay, so we're going to move on to descriptive statistics here. And this is super easy. What is descriptive statistics? You have a list of numbers, and we're just going to summarize them with either a number, like the mean, the median, the mode, the standard deviation, or with graphs, like histograms is the main one we're going to use. You can use bar graphs, whatever. This is what you've done. I'm sure most people have done this already. We're not making any inferences, okay? So let's just look at the descriptions here. So the mean, the mode, and are measures of the center of a distribution. We're not doing inference. We're not doing sampling. So we're basically, imagine that a list of numbers, these were the whole population. So if they're the whole population, we use this Greek letter mu to mean mean. If you're talking about a sample, you have a sample, then we use Roman letters. So we would use, we would use X bar. Let's not worry about this now. Well, maybe you should. Okay, so parameters are numerical facts about a whole population. So we're not even talking about sampling, so you don't have to worry about samples here. We have the whole population. Okay, so we're going to be using Greek letters here. So we'll use mu for average, meaning mean. Mu, mean, they both sound like an M. And standard deviation, sigma. Standard deviation sounds like S, sigma. Okay, later we're going to be doing sampling. Later we're going to do inferential statistics. So when we talk about inference, Then we say statistics are numerical facts about the sample, statistics sample, both begin with S, and are estimates of the population parameters, both begin with P. Okay, and then we use Roman letters, X bar and S for the mean and standard deviation. Mean is the same thing as average. Okay, so what do you do? So what is the mean? You just add up all the numbers and divide by however many there are. So if you find the average, you add them all up and just add all these up and divide by 7 because there's 7 of them. And what do you get? -1, right? Sorry, I messed up. That's equal to -7 over 7, which is -1. Okay, now just add up the numbers. Median. To find the median, what do? It's the middle number, so you list them in order, -5, -5, 0, 0, 0, 1, and 2. You list them in order, and then it's the middle number. So there's 7 of them, so the middle number is 0. What if there was an even number, like here? If there's an even number, what would we do? There's 2 middle numbers. So the median is halfway in between, the average of the 2. It's halfway in between, so it's 6 plus 10 divided by 2, which is 8. Okay. Now the mode is just the most common number on the list. So the mode is the most common number, so the mode is 0 here. All right. I think you all knew this before, so let's just turn the page. Now, properties of the mean. The properties of the mean are what? If a constant is added or subtracted to all the numbers on the list, to find the new mean, just add or subtract that constant. Okay, so try this with an easy example. Okay, so let's say you have a list of numbers. Let's make one up. 1, 2, 3. That's our list of numbers. The mean is what? You add them all up. It's 2, and the mean and the median are the same here. So what happens if you add, so we'll say add 5 to every number. If you add 5 to every number on the list, then what do you get? 6, 7, and 8. And then, of course, it's the same as adding 5. The median, the mean and the median both get increased by 5. So 7 and 7. I mean, you're just shifting the numbers up, all the numbers up. Think of it as just shifting the whole list of the numbers up. It's going to change the mean and the median. All right? Now, what if you multiply them? Let's do the same thing. So let's say we multiply all the numbers on the list. Multiply each number by 2. So we start off with 1, 2, 3. And we get, what happens then, if we multiply, they're going to get more spread out, right? It's going to be, and they're each going to be 2, 4, 6. So if we multiply by 2, then each number is, the mean is still 2, the median is 2 here, and you multiply by 2, and you get a mean equal to 4, and a median equal to 4. So basically, if you just, I feel like this is so easy. You know this on your own. I feel like it's embarrassing to teach it, right? How many people think that way? Raise your hands. How many people want me to go slower? Okay, that's good then. All right, so basically, if you multiply every single number on a list by the same number, then the average, or the mean, is going to get multiplied by that number, and so is the median. All right, now, so where does it really change? Where are the mean and median will result in different things? The mean is sensitive to extreme values, and the median is not. See what happens to the mean and median if you add 20 to the largest number on the list. So now we're going to take 1, 2, and 3, and we're going to add 20 to the largest number, only to just one of the numbers. Well, then what do we get? We get 1, 2, and 23. So now your mean here and median was equal to 2, And what happens? Your median is still the middle number. It doesn't change because it's not affected by what happens to extreme values. That stays the same. But the mean is going to rise because now you have what? You have 26 divided by 3, right? Which is 8 2/3. So it jumps up. All right, so it really gets affected by that. And then the last thing, I better just let you go now, but I just want to say this is relevant for like if you're looking at income. Like if somebody who's super rich walked into here right now, like Bill Gates or something, he wouldn't affect our average income, but he wouldn't affect our median income, but our average would zoom way up. The average is like putting everybody's money together and then evenly dividing it. Okay, so have a great weekend.